do another example. So in this example, we have a 50-liter reaction vessel. It has 1 mole of nitrogen gas, 3 moles of hydrogen gas, and 0.5 moles of ammonia. We're given a KEQ of 0.5 at 400 degrees C. So in this case, the temperature is not needed. It's just extra information. The question is asking, will more ammonia be formed when the mixture goes to equilibrium? So you will need to be able to write the formula equation given the word equation. We've got nitrogen gas plus hydrogen gas in equilibrium. Remember to write your equilibrium arrows with ammonia. We have to balance it. So this was given in moles. We need to change it to molarities. So just go ahead and calculate the molarities. So let's look at the Q expression. Remember, Q expression is set up the same way as K, but we just don't know if it's at equilibrium or not. So we'd have ammonia on the top, and then we would use our 2 here to get our 2 here. We'd have nitrogen gas on the bottom and hydrogen gas on the bottom. And again, remember to use your exponent. Now we plug in the values of our molarities and we get a number. For Q, it's 23.1. Well, 23.1 is larger than 0.5. So therefore, the Q is larger than the K, and the reaction will shift to the left. So we're saying that our reaction is going to go to the left. That means it's going to go this way. So you are not making more ammonia, you're actually losing ammonia. So the answer is no. But you need to show all the work. You couldn't just say no and get points. Okay, so now the question is asking us, it's for the same reaction. If instead the ammonia was 0.0001 molarity, the nitrogen was 5 molar, and the hydrogen was 0.01 molar, what direction would the system shift to reach equilibrium? So again, we set up our Q, we put in our values, and we solve for Q. In this case, the Q is 0.0020. The Q is smaller than the K. That means the system will shift to the right. So you could say for your answer, the equilibrium would go to the right. Okay, we're going to look at the very best way to organize the information in a problem to solve for whatever is being asked for. We're going to set up a table with the initial, the change, and the equilibrium values. I call these ICE tables. So let's look at a problem and how we would set up our ICE table. We have the reaction of gaseous hydrogen fluoride from hydrogen and fluorine. And these are going to be gases. We're given an equilibrium constant of 115 at whatever temperature. And in that particular experiment, we're adding 3 moles of each component to a 1.5 liter flask. So first you want to set up a table and label it. So this is going to have your reaction, which is balanced. And then here's your initial molarity, your change in molarity, your equilibrium. There's your I, C, E. So calculating the moles over the liters, we would get the molarity of the hydrogen gas as 2, the molarity of the fluorine gas as 2, the molarity of the hydrogen fluoride as 2. So if we look at our equation, we have 1 hydrogen gas and 1 fluorine gas to make 2 hydrogen fluoride gas. So that's why if we're going to have a change, we're going to have these reactants become a product. We would mathematically say minus x plus 2x. We obtain 2 hydrogen fluoride molecules every time we lose 1 hydrogen molecule and we lose 1 fluorine molecule. So now we have our directions. We just follow these directions as to what to do. 2 minus x, that's how we get this. 2 minus x, that's how we get this. 2 plus 2x, that's how we get this. We're losing reactants and we're gaining a product. That's why this is a negative, minus, a minus because we're losing. This is a plus because we're gaining. So the equilibrium is going to be this last row. We're going to set up the KEQ expression and then put in the values from the equilibrium portion of your ICE table. So our KEQ was 115. It's products over reactants. I remember that this was your coefficient. And then this is our equilibrium expression. We put it in where it belongs. And then this is our equilibrium expression. We put it in where it belongs. Equilibrium expression, put it in where it belongs. And now you are going to have to be able to do the math. In this particular example, if I take the square root of both sides, that will simplify matters. So in other words, I took the square root of this, that's what I got here. Take the square root of this, then you get this. Take the square root of this, then you get this. So you will, in this particular case, take the square root of both sides. You end up solving for x, and when you do that, you now have a value of x that you can use, and you have directions in your ICE table. Your ICE table told you that once you get x, you subtract it from 2, and you get the hydrogen gas concentration. The same for the fluorine gas. Once you get x, you subtract it from 2, and you get the fluorine gas concentration. And then in this case, you're going to just follow your directions. You have to subtract 2x to get your hydrogen fluoride gas. Okay, that's good for now.